Okay, good day everybody. This is my short video on making maths visible that I'm creating for the Lumen CPD project. And what we're going to talk about today is using models and structure in place of rules. My name is Peter Mattock. I am an assistant principal at Brockington College, which is an 11 to 16 school in Leicestershire. I also work as the secondary mastery lead for the East Midlands South Maths Hub. I'm on Twitter, and you can tweet me at Mr. Mattock, and you can also have a look at my website, which is visiblemaths.co.uk. And one of the things you'll find there is a link to my book, which is also called Visible Maths. So if you are interested in using models and structure and representation to support learners with making sense of mathematical concepts, then please feel free to have a look at that, and you might find it useful. So we're going to talk about models and structure. And what we're going to talk about is this is potentially the view of mathematics that some learners will get as they sort of progress through the maths curriculum. And you see different ideas coming back and forth, but seemingly these dots are just all over the place, and this can be quite disconcerting for learners. They think, well, I've just got to remember all these different dots and all these different positions and blah, 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 blah. But when you reveal to them the underlying structure, they can see how these different dots connect to each other and make sense as part of the larger body of mathematics. So what we're going to look at today, and what I'm going to look at today, is just potentially a couple of mathematical ideas and how we can use models and structure in place of rules to support pupils in making sense of them throughout the curriculum. And the first idea, the first concept that I'm going to look at is addition. And here are some arbitrary rules that we might use with pupils, or pupils might be aware of when it comes to addition. So first of which, when we add large numbers, when we add numbers that have more than one place value column, then we add the ones column first, and then the tens, and then the hundreds, and we keep going, bigger and bigger columns every time. And this gives rise to potentially methods, procedures that look like this. And then we add the ones, and then we add the tens, and we carry one because that's what we do. And then we add the hundreds, not forgetting that extra 100. And now we don't have to carry one. It was just 13 that time because that one is 1,000. And you can see how that might be potentially difficult for pupils to make sense of what is happening there. Or we might, there might be a picture that looks like this. I mean, 25 add 9 as column addition. Sure, why not? Yeah. Or even we break it down and we use words for the units. 5 ones and 9 ones is 14 ones, and we regroup that with the extra 10 that we have, and to give 2 tens and 4 ones. And, all of this is just sort of, you can understand why pupils might struggle to make sense of it. And then we come on to other rules. So there's this order of operations that we have where we've got powers and roots at the top and other functions technically as well, supposedly. Then multiplication and division, then addition and subtraction at the bottom. And why is that? Well, we don't need to know why that's the rule. That's the hierarchy. Except, of course, we do need to know why. And there is a good reason why that happens in the way it does. And that leads to things like this. I don't use that word in my classroom at all anymore, and I would urge people not to use it as well, because not only is it not helpful a lot of the time, it's actually mathematically incorrect. You get versions of this, all variations on the theme. PEMDAS is an American version of it mainly. It's used a lot in America, with "please excuse my dear Aunt Sally" to help remember it. Oh, we get another version. This is a different version, brackets and then orders, which is apparently another name for powers. And again, we have to, one of the important things here is, well, how is this linked to what I was doing with addition before? If addition's in here, and we were talking about addition before, how does this link to that? How does that make sense? This is a recent one. Gems. grouping symbols, then exponents, where roots are in there. I don't know. Do you have to learn that root is power a half before you can fit it in? The square root is power a half, I should say, and then multiplication and division, and then subtraction and addition. Subtraction comes before addition that time. Okay, if you say so. And then, of course, we come on to adding fractions. Add and subtract fractions, they must have the same denominator. That's true. That's a rule. But why? Why is that a rule? Why is that necessary? Why is it suddenly important they have the same denominator? That's not happened with addition before. Okay, I've been trying to add fractions, but what is it about addition that means they have to have the same denominator? And these are all rules that pupils may have come across that may have been presented in a relatively arbitrary way. It's just, this is a rule of mathematics that you have to follow all the time. And in fact, if we think about these things and we look at these things and we look at what addition is and we look at what fractions are and we look at what other operations and how they appear and how we make sense of them, then actually these rules are not arbitrary. And we can see how they fit into the larger concept. We can see how that circle for addition, with the dot scrolling around it as it bumps into fraction and place value and other operations, we can see how that all makes sense. And that's what I'm going to sort of look at with this. And you get, when you talk about these arbitrary rules, you get horrible pictures like them. There's so much wrong with that in terms of both efficiency, but in terms of, what it is that's actually happening. You're not multiplying 4/6 by 9 there. It's not got 9 times bigger. You've not got 5 9s. You're not making that 6 times bigger. This is an old method, or old to me anyway, method for adding fractions called the Battenberg method, where you have your 2/3 across the top and you have your 3/4 down the side, and you're adding them. So your top left box is add, and in the top right box you do 3 times 3, and in the bottom left box you do 2 times 4, and then you add those together and write it over the denominator that is 3 times 4. Or you get the butterfly method, which is a very similar sort of thing. But again, all of these methods, they don't look like addition, do they? When else does addition look like this? How am I supposed to remember that that's what I do when I add these particular things, rather than become aware of sort of what property is it of addition that means that this is going to be required, or something like it is going to be required? So let's have a look at these, not through sort of arbitrary rules, but through models and structure instead, and how they will work together to support us. And a lot of this, and a lot of what we're going to talk about in both areas of maths, both concepts that I'm going to talk about today, comes back to how we see number. And how is it we can think about numbers, and how is it we can make sense of numbers? So we're going to start very simply. How do I see the number 4? What are good models, good representations, good ways of thinking about the number 4? Because if I think about numbers in the right way, then I can begin to think about in useful ways. There's no right way, but in useful ways, then I can start to think about operations on those numbers and what they might look like and how I may make sense of them. So for the number 4, we might represent that as 4 objects. 4 counters, 4 little squares, 4 cubes, but 4 objects in some way. We might actually represent that as a single object worth 4. And this is a transition that learners make at some point, the sort of one-to-one representation where each object stands for 1 to objects standing for multiple numbers. So contained within that single object, there are 4. It is worth 4. We could look at length or area to represent 4. And here I'm using Cuisenaire rods to sort of show that, and show how 4 objects has the same area as this bar of 4, or the same length. And you can, because they have same width of 1, you can consider length and area together there, but this has a length of 4, an area of 4. It's a representation of the value of 4. Or if the white rod wasn't 1, well, what if the red rod was 1? If this is worth 1, then suddenly this becomes worth 4, and this is important as well in the idea of numbers being defined in their relation to the unit, the 1. And depending on what we see as 1 will depend on how we see other numbers potentially. And we might do that on a number line using a vector or just using the number line itself. This vector here has a length of 4, so it's 4 units long. It's worth 4. So is that one, though. That's also a good representation of 4. It's exactly the same length as this green one. It points in the same direction. These are particularly useful, as I'm sure you can appreciate, for directed number potentially. And if we start to see numbers in useful ways, then we can start to consider, okay, well, what does it mean to operate on these things? How do I make sense of operations regarding these numbers? And so we can start quite simple. We can start with something like 4 plus 5. We can say, well, I know what 4 looks like. And if I know what 4 looks like, I can potentially extrapolate what 5 looks like. And that might look like that. Well, there's 4. I can see 4. And that must be therefore be 5. That makes sense for that to be a representation of 5. And so what does it mean to add these things together? Well, in this context, what it means is I'm going to collect these things because they're all the same value. They're all 1s in effect. This is 1, 2, 3, 4, 1, 2, 3, 4, 5. I can collect those together because they have the same unit value. And that means I have 9 of those things now. I have 9 1s. I could do the same thing with the Cuisenaire, and I could use the white rods as 1 to show the 4 1s and the 5 1s. But then I could go further and say, well, then this must be 4 because it's the same length as 4 1s. And this must be 5 because it's the same length as 5 1s. So what does it mean to add them when they look like that? Well, it means connecting them to find their total length or their total area, depending on what measure I'm using to represent the number at that point. If it's length, it's the total length of 9. If it's the area, it's the total area of 9. And I can move fluidly and flexibly between those potentially once pupils have got a good grounding on what how I'm representing these numbers potentially as length, potentially as area. And I could do something on the number line. I could say, well, I can see what 4 looks like, and I can see what 5 looks like. And again, we get this idea of connection. Connecting these one after the other, 4 followed by 5 more. And these are all good ways of thinking about addition, of making sense of addition. And they come from what I know about numbers and how I see numbers. And in fact, these models allow us to make sense of all of those additions that we potentially might have introduced using arbitrary rules, and all those things involving addition that we potentially might have introduced using arbitrary rules before seeing this sort of thing. So once I've got a good grasp on what addition looks like as this collecting of things with the same unit or connecting these lengths or areas, then I can start to look at other additions involving larger numbers like 444 and 555. And I can represent that number now. I could represent that number potentially like this, using a sort of one-to-many counter representation. Now I have counters that are worth hundreds and tens and ones. And I have other counters that are worth hundreds and tens and ones. And I've got my 400s, 40 and 4 here, and my 500s, 50 and 5 there. And when I look at something like that, I can see, okay, well, I can collect together the things that are the same. So I can collect together my hundreds, and I can collect together my tens, and I can collect together my ones. And importantly, when I look at that, I might start to see that actually it doesn't matter what order I collect those. I could do those in any order. I could collect the tens first, and then the hundreds, and then the ones. I could collect the ones first, and then the tens, and then the hundreds. I could collect the hundreds, and the tens, and the ones. I could collect the hundreds, and the ones, and the tens. It makes no difference in this case to what I will arrive at, which is, of course, 999. But if I now look at an addition like this, 454 and 455, well, then perhaps the situation is not so clear, because now if I collect together my hundreds, I've got 8 hundreds, that's fine. And if I collect together my tens, I've got 10 tens. And if I collect together my ones, I've got 9 ones. But I don't have a number which is 829, do I? 829. That's not a number I'm familiar with writing. And before we move from something like this, 444 and 555 to 454 and 455, pupils have to be familiar with the idea of exchange and regrouping. And, you know, that might require a bit of work. And it might be that I do calculations like this, or I look at calculations like this, and I don't look at calculations like this for a little while. And I do that work in between, that work around place value. But once that work is done, then we can make an argument that says, well, in this case, actually, it would make sense to collect from the lowest power of 10 up to the highest power of 10. Because now if I am collecting from my lowest power of 10, if I reach the point where an exchange is required, then I'm doing that exchange before I've evaluated what I'll be exchanging into. So if I look at this now, starting with the lowest place value column, I can see, right, well, I collect these ones. There's 9 ones there. There's no problem. I collect these 10s, and there's 10 10s now. And I know, because I've done something about place value and I'm familiar and fluent in that area, that those 10 10s are worth the same as 100. So I can evaluate an exchange there before I've evaluated my hundreds, because I know I might gain some extra ones, and it makes sense for me to do it in that order in this case. And so I exchange my 10 10s for an extra 100, and now I look at my hundreds and I say, right, well, I have my 400s from before, and I have my 400s from my second number, and I've got this extra 100 which came from exchanging the 10 10s. So now I've got 900, and I've got no 10s now, because all of my 10s were exchanged for 100, and I've got 9 1s, so I have 909. And in that case, it makes perfect sense to work from lowest place value column to highest place value column. But that's because an exchange might end up giving me more of the next place value column up. And I recognize that, and I can see how that makes sense. And so I can see why in that case it's a good idea to do so. But it's not a sort of rule for all additions. It just helps with having to reevaluate. If I go back and I were to do it the other way around, I would have to evaluate this as 8. And then I'd say, oh, but I've got 10 10s, so now I'd have to cross out that 8 and change it to a 9. And it just helps in sort of neat recording of my evaluations if I start from the lowest place value column and work up. And I may choose to do that every time. I may just choose to do that at the times when it's clearly required and I can identify that it's required. But it's not a rule for addition. It just helps in certain places. And part of becoming fluent with addition of numbers with multiple place value columns is actually starting to recognize that and saying, okay, well, I can see why that's a useful thing here and potentially is not so important here. And then from there, we can go on to look at multiples, multiplication and addition combined. And we can use a very similar idea here. We can say, right, well, instead of having hundreds, tens, and ones, I've got 3s. And I've got 4 3s, and I've got 5 3s. And because they all do have the same unit value, I can collect those together. That's fine. And this, for me, is what puts the death knell in the bid mass idea, in that there's no reason for me to multiply those before I add them. I am perfectly at liberty to add those things. I have 4 3s, I have 5 3s, I add them together, I have 9 3s. There's nothing wrong with that at all. That fits with the structure of addition and with what I know about addition and with how addition works, how I make sense of addition. And I could show the same thing using the questionnaire in potentially a couple of different ways. I could show that 4 3s here, 3 4s technically, 3 by 4 and 3 by 5 can be connected together into 3 by 9. And I'm looking at the areas now there. I'm saying this is a 3 by 4 area. This is a 3 by 5 area. And I can connect those to make a 3 by 9 area. Or if I wanted to look at length, purely at length, I could say, right, well, here's 3 4s and here's 3 5s. But that's the same as 4 3s and 5 3s. And that's a total length of 9 threes. So this has a total length that's the same as 9 threes. And I could do that on a number line. I could say, well, because I'm doing 4 threes and 5 threes, I could actually graduate my number line in threes and show 4 threes, 1, 2, 3, 4, and 5 threes being connected, because addition looks like that. I can see addition like that being connected to make 9 threes. But if I come to something like this, 4 threes add 5 twos, well, then the situation isn't so simple. 4 threes and 5 twos. In that form, looking like that, with my unit of 3 and my unit of 2, I can't add those together in that form because they don't have the same unit. I can't see what I have when I collect those. However, what I might do here is I might say, right, well, I know 3s and 2s can all be exchanged for 1s. So I'll exchange my 3 for 3 1s, each of my 3s, and I'll exchange my 2s. And now I've got 1s. Now they're all 1s. I can add them together. And so in this case, yes, I do need to potentially evaluate each multiplication separately to find out how many 1s that's worth before I add them together so that they're in a common unit. Because I need them to be in a common unit in order to add them. I know that about addition and I've made sense of that idea from addition already. Or I could again look at it using Cuisenaire and see, 4 3s and 5 2s and see 3 4s and 2 5s if I prefer, or any mix of those two. And I can see that this time I don't get this sort of single rectangle. And it may be that if I want to find out what the total area of these shapes is, that it makes sense to evaluate the area here and evaluate the area here and then add those 2 areas together, or evaluate this number and evaluate that number and then add those 2 together. That would seem to make sense in this context. Or I could look at it on a number line and say, because my first things are going to be 3s, I'm going to have a 3, a 3, a 3, a 3, and then I'm going to have 2s. I can't actually graduate my number line in either 3s or 2s, or 4s or 5s if I want to switch it around. I have to graduate my number line in 1s in order to see that. So I can see that my 4 3s is 12, and then my 5 2s is the extra 10 that I'm connecting on. And any of those might help me make sense of why, in this case, I have to complete the separate multiplications potentially before I add, whereas in this case, I don't have to. And I can start to see again where multiplication does have to be evaluated before addition does, and where it doesn't, importantly. And then I can keep going with addition all the way through my curriculum. I can have 0.4 add 0.5, and that would potentially look something like this. We can see 0.4, again, just extending the idea of the place value counters now, but to parts of the whole, to place value columns that are less than 1. And so I have my 0.4 and my 0.5, and I can clearly add those together because they all have the same units, 0.1234, 0.12345. That gives me 0.9. And there's no issue there. I know all about addition by this point, and I can see that I can collect those, and that's fine. Or I could say, right, well, we're used to perhaps different rods having a value of 1. So if the orange rod is 1, then this is 0.4, and this is 0.5. And connecting those together gives me something that's equal in length to 0.9. It's 1 less than 1 whole. It's 0.9. I could actually use the blue rod there to show that that's equal in length to 0.9. Or I could do that on a number line and say, right, well, let's graduate my number line in 0.1s. And I have 0.4 and 0.5, and that gives me a total of 0.9. And I can go for multiple columns, not just things of the same column. Here we are. There's 1.52 add 0.3. And we know potentially that, the most common mistake here would be for kids to write 1.55 and just add the 3 to the 2 because it's the last number in each. But actually, if I'm representing those numbers and if I understand something about addition, then I can see that actually that 0.3 needs to be added to the 0.5 because there are the things with the same unit value. So 1.52 add the 0.3 becomes 1.82. I can use my Dinesh blocks for that with area and do the same thing. If this blue represents the value of 1, then this is 1/10. So this whole green area here is 5/10, and this is 100th. So this is 200. So 1.52, and then this is 0.3. And I can do exactly the same thing. I can connect those together to create that overall area, which has a value of 1.82. I wouldn't necessarily do that one on a number line because number lines graduated at hundredths there make it quite difficult to show one. And from there, I might well transition into fractions, or I might do fractions first. I might do fractions before I do decimals. It doesn't really matter. It's the structure that's important. The fact that it's the same structure means that the order of these things can be driven by other considerations, like am I going to explore decimal place value before I explore fractional value, or which way around am I going to do that? But when it comes to when I'm ready to add these things, well, this is no different. This is exactly the same as addition always looked. Here I've now got 4/11ths and 5/11ths. They all have the same unit value. I can add those together. And at no point can the idea that that's 9/22 even come into play. My things are 11ths. I have 4/11ths. I have 5/11ths. The name of this, literally the denominator, the name, denom, is 11th here. So I have 4 of these things. I had 5 of these things. I add them together. I'm going to have 9 of those things. And then I could do the same thing with Cuisenaire by saying, right, well, what if this is my whole? Well, if this is my whole, then this is now 4/11ths, not 4/10ths or 4. It's 4/11ths, but it's 4 somethings. And it's a 5 something. And when I connect those together, it's going to be a 9 something. And in this case, the something happens to be 11ths. And I could do the same thing on the number line. 4/11ths, 5/11ths. My marks are now 11ths rather than 1s. But you'll notice these arrows were the same size as they were when they were 4 and 5. Or 4 3s and 5 3s. And if I come to 4/9 add 5/12, and I've put the picture in for 4/9 add 6/12, so we're going to ignore this last 12th here. 4/9 add 5/12. I can't add those. I don't know I can't add those because they don't have the same unit value. There's no consideration that that might be 9/21. I'm adding things with different unit values. I can't do that in that form. And I know enough about addition now to know that I can't do that in that form. But I can if I've done something with fractions. And again, there might be a big gap between here and there. But if in the interim between those things, I've worked a little bit around equivalent fractions, and I know that every fractional value can be written as an infinite number of different equivalent fractions that are the same value, just written differently, then I might reach the point where I can see that, well, actually, if I want these to have the same unit value, then it would make sense to turn them into 36. Again, ignoring this last column here, I can see that each of my 4/9 has been turned into 36, so I'm going to have 16 of them. And each of my 12s has been turned into 3/36, so I'm going to have 15 of them. And that's going to give me the total 35/36. I could do the same thing with the Cuisenaire. I need to set up a whole, and again, a lot of fractional work needs to be done in between, where I'm going to set up a whole that will allow me to display both 9ths and 12ths. Well, if this is my whole, then each of these purple bars is a 9th because it would take 9 of them to get across to my whole. And each of these green bars is 12ths because it would is a 1/12 because it would take 12 of them to get across to my whole. And so I can add 4/9 and 5/12. I can connect those things together and I can look at what I have all together. This is clearly, if the white rod was 1, this would be 36 long. This is 31 of those 36. You can do the same thing on a number line. Whether you graduate the number line with simplified or unsimplified fractions depends on yourself and depends on your learners, but you can do the same thing with a number line as well. When it comes to 4 add -5, then the situation has to be tweaked a little bit, because that might look like that. And you might at first say, well, we can't add those together then because they're not in the same unit. However, there is a special case, and there's no getting around it. It is a special case because it's one of the axioms of maths. It's one of the field axioms. And the field axioms say that for any positive number or any number, there exists its negatives such that when you add them, they make 0. So they're allowed to be added even though they don't have the same unit value. One is the negative of the other, because their result is 0. And if we introduce that, and pupils are fine with that. Pupils are fine with tweaking that for this one scenario. Then we can see that that will all be 0, and I'll be left with -1. We can do the same sort of thing on the number line. Here is 4. This is -5 because it's like 5, but it points in the opposite direction to 5. And if I connect those, and you might even loop that around there, so one arrow ends, the next arrow starts, but if I connect those, I end up at -1. No such requirement for -4 add -5, though. Those all have the same unit value, -4 and -5, and the result of that is -9. And again, you can see that on a number line. There's -4, connected to the end of it is -5. And the total resultant is -9. The point here again, addition always looks the same. There is this limited number of ways I'm modeling the numbers, and I'm thinking about the numbers, and whenever I think about the numbers in these ways, the addition looks the same. We get to surds, exactly the same thing. I probably don't even need to show you at this point. You can probably see automatically 4 root 2s, 5 root 2s, all have the same unit value, 9 root 2s. A bit more difficult to represent that one on the number line. What about 4 root 8s plus 5 root 2s? Well, not in that form, not the same unit value. But we've dealt with things like that already. Particularly, we've dealt with where one of them is one or both is exchangeable. And in this case, again, potentially lots of work done between the two about simplifying surds and being able to convert the form of surds to be able to see that root 8 is the same as 2 root 2s. And so each of my 4 root 8s becomes 2 root 2s. So in the end, I have 8 root 2s here, plus another 5 root 2s. So I'll have 13 root 2s. And of course, what we're talking about is this general structure. And this is where ultimately all other additions come from. This general structure that 4x add 5x all have the same unit value. That's 9x. And I can show that with algebra tiles, which is sort of the generalized form of the Cuisenaire rod. 4x add 5x connected together. I could show that with vectors. I could scale that number line in x's if I wanted to, or I could just mark them on the lengths. But when it comes to 4x add 5y, no joy. Don't have the same unit value, or I can't make any sense of how long this is in terms of just x or just y. Again, I could now offer something like saying, well, what if x was worth 2y? And then we might be able to do similar sorts of exchange, and we're paving the way there for exploring things like simultaneous equations, where we can do an exchange and then I could add those together. But in that form, there's nothing else I can do. It's just 4x add 5y. So this is just one example for how good models for numbers, for addition, and recognizing the structures at play mean that actually all of those arbitrary rules no longer required. Instead, what we've got is we've got these different numbers, different types of numbers, obeying that structure, fitting with that structure. So that structure, that concept of addition, looks the same, is the same at all points through a learner's journey. And that circle that represents addition with that dot coming around it as it bumps into fraction, decimal, surd, algebra, in whatever order that it makes sense to do those things. is recognizably still part of that circle, part of that structure. There it is again with the algebra tiles. Don't know why that was animated a little bit later, but there we are. Very quickly then, we'll just run through another one. I'm aware of time, but we'll just run through another one, which is around factorizing. And same sort of idea. We get rules. Take out the 4n, take out the highest common factor. Okay, why? Why is 4n the highest common factor? Is 4n always the highest common factor? Doesn't that depend on the value of n? Prime factors. Oh, we use a tree for that. It's the only time we ever use a tree for factors when we're dealing with primes. But we use a grid when we're doing quadratic factorization. So this same word appears 3 different times. And every time the thing I do looks different. Is it any wonder that kids struggle to remember it? So instead, the structure behind factorizing, I'm going to use my Cuisenaire rods for this. And my prompt is going to be simply, build a rectangle. Now, I'm aware they're 3D, but they look 2D for our purposes, so it's fine. Build a rectangle with no gaps and no overlaps with a value of 8. So I'm going to flip over to my Cuisenaire rods now. Here they are. And I'm going to do that. I'm going to build some rectangles with a value of 8. I'm going to build this rectangle. And I'm going to build that rectangle. And I'm going to build this rectangle because I can. And there's a whole host of different rectangles I could build there. But what do I notice? Well, I notice that any rectangle I could build is either a 2x4 rectangle or a 1x8 rectangle. And from here, I get the idea of the factors. Yeah, the factors of 8 are 1 and 8, 2 and 4. And I can decompose 8 into a product of factor pairs in 2 different ways. 2 times 4, 1 times 8. And those are the only way I can decompose 8 into a product of factor pairs. And so now, having looked at 8, I might look at 12. I might look at 9 because that's square. I might look at 13 because that's prime. But the idea of factors and factorizing stays the same. Build me a rectangle, no gaps, no overlaps. How many different unique rectangles can you build? And when it comes to prime factorizing, I might say, okay, build me a rectangle, no gaps, no overlaps, with a value of 18. Look at their factors, look at the lengths and look at their widths. And in particular now, how can you create those lengths and widths using only prime valued rods? So if I now build 18, there's a couple of ways I might build 18. I might build 18, I'm just going to do some simple ways. I might build 18 like that. I might build 18 like this. I might build 18 like that. And I get 2x9 or 3x6 or 1x18. And so now what I'm saying is, okay, can I create those lengths and widths using only prime valued rods? Well, I can definitely create this width using only a prime valued rod. That's 2. This 9 then, I can't just put a 9 there because that's not a prime value, but I could build that with 3 3s. So what I've got here is what was 2x9, that 9 being replaced with 3 times 3. And that gives me 2 times 3 times 3. That gives me the prime factorization. It allows me to see how that factorization is linked to the idea of primes. And, I could draw a tree for that now. I could say, right, so we took the 18 and we broke it into 2 times 9. That was the decomposition. And then we took the 9 and we broke the 9 into 3 times 3. We didn't have to do anything with the 2 because it was already prime. I could just write that as a line-by-line decomposition. 18 equals 2 times 9, and then underneath that, 2 times 3 times 3. How I record that will depend. But this is how it ties to the structure behind factorization. And when it comes to the 3x6, well, I could do that. I can make that 3. And then I've got actually choices how I make this length of 6. I could make this length of 6 using that prime valued rod, or I could make that length of 6 using those prime valued rods. But either way, what have I done? Well, I've gone 3 and then 2 times 3, or 3 times 2. But that's the same decomposition. 3 times 2, 2 times 3, it's the same decomposition. However, if I start with the 1 by 18, well, then I run into a difficulty, don't I? I don't have a prime valued rod that will fit along this width. And that's showing me that decomposing 18 into 1 times 18 is not going to help me if I'm going to talk about prime factorization, because I could carry on decomposing 18 as 1 times 18 forever. 1 is not prime, so it's not going to help me. But the 2 by 9 and the 3 by 6 will be. And eventually that will lead to the idea of trying to make non-unit widths and potentially, eventually, the largest width. So that when I then come to algebraic factorization, and for this I'm going to use the generalized Cuisenaire wad, I'm going to use the algebra tiles, and the algebra tiles look like this. We've got our 1s, our x's, our x squareds, our negatives of those. Then now it's, well, can I create a rectangle, no gaps, no overlaps, with an area of 3x plus 6? So I take 3 x's and I take 6 1s. That's 7 1s. Take 6 1s. Can I create a rectangle, no gaps, no overlaps with that? Well, yes, I could. I could just do this. And I could then line all my 1s up. But just like with the primes, all that's telling me is 3x plus 6 equals 1 times 3x plus 6. And that's not particularly helpful. So instead, what else might I do? Well, the other thing I might do is this. I could create this rectangle with no gaps and no overlaps. And now what do I have in terms of the length and width here? Well, I have a width of 3 and I have a length of x plus 2. And this is, of course, the beginnings of the grid method in inverted commas, because it's not really a method at all. It's just a picture of what I've seen there. I created an area, 3x plus 6, with a width of 3 and a length of x plus 2. And so my decomposition here is 3 times bracket x plus 2, or 3 bracket x plus 2. And I could explore some other ones. I could explore 6x plus 3, 6x plus 9. I could explore 6x minus 9 using the counters there, using the negative versions of those, not the counters, the negative versions of the tiles. I could even look at 9 minus 6x using the negative versions of the x tiles. And then when we come to further algebraic factorization, I might say, well, now let's bring in the x squared. Can we create a rectangle, no gaps, no overlaps, that uses x squared and 5x and 6? So again, if I do the same sort of thing, I have my x squared and 5x's and 6. Can I create a rectangle with no gaps and no overlaps here? And yes, I can. And I can start with my x squared. And then what I might draw attention to are things like, well, I'm not going to be able to line my 1s up along either length here, because these lengths are x. And you can see the x's and the 1s don't line up well against each other. So I'm not going to be able to line my 1s up against either of these. So if I'm going to create a rectangle, well, I'm going to have to put my 1s down here. And then it's a case of, okay, well, I'm not going to be able to put my 1s, say, like this, because there's no way I'd then fill in those gaps. So I'm actually going to have to create a smaller rectangle just out of my 1s. And what might that rectangle look like? Well, of course, it might look like 1 by 6, or it might look like 2 by 3. And which of those will allow me to fill the x's around my x squared and around my 1's rectangle to create a complete rectangle? And of course, in this case, it's having the 2 by 3 which will allow me to fill in those 5 x's to create the complete rectangle. And then again, it's a case of, okay, so what's the length, what's the width? What's the decomposition here? Well, I can see now that the length of this is x plus 2, and the width is x plus 3. And so there's the decomposition. And again, you know, this might lead into a picture that looks like a grid for something like this, and eventually, hopefully, into complete abstraction. And again, I could explore some others. So I could explore x squared plus 7x plus 6, x squared plus 7x plus 5x minus 6, minus 5x plus 6, minus 5x minus 6. So that was my video on using models and structure rather than arbitrary rules to support pupils making sense of these mathematical ideas as they reappear through the curriculum, how they connect together, get that sense of coherence within an idea and across ideas. And if you found that interesting, then there are lots of other places that you might go to sort of further your knowledge on that. And one of the main places I would suggest would be to look at my YouTube channel. And my YouTube channel, again, is linked through my website. You can see the address at the top, youtube.com/cpetermattock. But it's linked through my website, and on there you can see I've done lots of videos in how we might support learners in making sense of these concepts using structure and models, manipulatives, representation, rather than just arbitrary rules. You can see some of the ones we've looked at here, quadratics and factorizing. We've looked at fraction a little bit, order of operation a little bit as well, but there are plenty of others on there as well. I think we're up to about 40 videos at this point. So you might well want to have a look at that. And again, like I say, you may well want to have a look at my book, Visible Maths, as well, because that contains many such areas where we can use representation, manipulative, and the structure behind an idea to help pupils make sense of it every time it appears in the curriculum. So that is my video. I hope you found that useful and interesting, and I'd just like to say thank you very much if you've managed to watch it all the way through. Thank you very much for your kind attention.